Hello again. In the following video, I solve Walter Lewin's 1000 GeV Large Hadron Collider problem. The problem was presented in the following way. One proton is in motion with respect to the Large Hadron Collider with a kinetic energy of 1000 GeV as measured by the Large Hadron Collider, and another proton is at rest in the Large Hadron Collider. The problem stated a completely inelastic collision which the two protons survive to move on together. The problem asked for the maximum rest energy that a created particle could have. Like several other students, I first calculated an energy difference of 1 proton rest energy. I had falsely assumed that both protons will survive the collision, ideally to carry away maximum kinetic energy. However, later in his video, Walter Lewin explained that the answer seeks the maximum rest energy of a created particle in a realistic collision. I therefore reformulated myself the question to ask what the rest energy of the created system would be after a total realistic collision in the Large Hadron Collider. I think that realistically two protons disintegrate, but we can assume the resulting system to also contain two protons that share some of the momentum of the system, but not as much as if the two protons would survive and carry on with maximum kinetic energy. Based on this reformulation of the question, I form my ansatz in the following way. Whilst m0 is the rest mass of any particle measured by the Large Hadron Collider when at rest in the Large Hadron Collider, the energy and momentum of any particle in the Large Hadron Collider measures according to the stated formulas, where v is the speed within the Large Hadron Collider. Both formulas for energy or momentum of any particle as measured by the Large Hadron Collider combine to the equation at the bottom of this page. But this equation then holds for any particle in the Large Hadron Collider respectively, which in our problem implies the in the Large Hadron Collider moving proton, the in the Large Hadron Collider resting proton, and the system after the total collision, which is equivalent to a new particle. But we can reformulate the latter equation to solve for the rest energy of the new system, which is the quantity we want to find. Employing total energy and total momentum conservation as measured by the Large Hadron Collider, we know that the total energy of the new system equals the sum of the energies of the colliding particles. The same holds for momentum, all as measured in the Large Hadron Collider. We formulate this out to the equation at the bottom of this page. But we now remember the equations for the energies of our two colliding particles, which we previously derived. We are substituting them in such a way to leave no unknowns. We then result in the equation displayed on the bottom of this page. When now substituting our numbers, we therefore get the correct result for the rest energy of the newly created system after a total collision in the Large Hadron Collider. From this, we can now subtract the rest energy of 2 protons.